The following experiments expand upon Antoni Gaudi's methods of understanding architectural form through the use of hanging catenary models. The first step was to build an apparatus that would provide a level datum plane to hang the strings from. Using two 10-foot PVC pipes and 4 PVC elbow joints, we created a 2-foot by 2-foot by 3-foot tall frame. 4 dowels spaced at 4-inch intervals on the x-axis and 4 more placed at the same interval on the y-axis were used for the base grid that served as the datum plane for each model to hang from. We compared the behavior of a plaster-water mixture and that of a glue-water mixture on cotton string as a solidifying material. The goal was to be able to freeze the forms acting in tension and later invert them to be forms acting in compression. Each material was tested on both a weighted and an unweighted string, as well as a fabric sheet and strips. We found the plaster was better at coating the string and keeping solidity than the glue, so we decided to continue experimenting using the plaster. In our first trials, we attempted to dip the string in plaster. This did not allow enough material to adhere to the string in order to freeze the form. Applying the plaster by hand, however, for about 5 layers with 10 minutes between the application of each layer, completely stiffened the string form. Catenary curves were formed by tying one end of a string from one point on the datum plane grid to another point. 3 or more strings were attached to the corner points of the model. Then those 3 individual strings split in different directions to be tied off to other points on the datum plane. This allowed for strings to cross over one another at what we are calling points of contact. When the strings were set up the way we wanted, we blended the plaster mixture and began applying it to the string by hand. Once the plaster had dried, we recorded the locations of each point of contact in the model using a 3D grid. This grid was formed by elements along the X, Y, and Z axes and used the datum plane grid as reference. To construct the X and Y elements that happen at different elevational levels, we built 2 sets of 6 horizontally oriented dowels, each at 4-inch intervals, and fixed them to either side of the frame. We were then able to lay more dowels across the frame from one of those ladder-like structures to the other. The vertical grid lines were then created by connecting the top base grid to a congruent grid on the floor using string. In addition to compression, we found that it did not support itself very well because the corner column supports gave way as soon as we placed it upright on the floor. To record the locations of the points of contact, the 3D grid was recreated in Rhino so it could be more simply viewed. The side-by-side comparison of the 2 sets of data brought us to 2 conclusions about why Model 2 was more successful. It has more points of contact and therefore less distance between those points, and it has a lower center of gravity.